Quickly about me, myself, Dinesh Venkatesan, also called as VL Dinesh. I work at Microsoft, and I'm basically a logician mathematician who applies graph theory in solving some of the security problems across cross-platform security research. And I have been building a knowledge graph of malware families targeting Android, Linux, Mac OS. So also all opinions expressed here are mine. Let's start with a couple of stories. One is about debugging a Heisenberg, and another one is an example of an analysis paralysis and how that is relevant to a malware researcher or a vulnerability researcher trying to establish or trying to find more about a malicious behavior. So, um, the story I'm going to talk about is written by Isaac Asimov, and the first one is "Catch That Rabbit," which deals with the concept of Heisenberg. Basically, Heisenbugs are those kind of bugs which disappears when somebody tries to debug them. When it is not monitored, the bug appears. When somebody monitors it, the bug disappears. And analysis paralysis is basically about how a bot, when any bot that has to obey three laws of robotics, like it cannot, if with three different priorities, and if the bot is not able to make a decision whether rule number one has to take precedence over rule number two, or rule number two over rule number three, it generally results in an analysis paralysis, and the bot will never be able to take a decision whether something is good or bad. So we can draw the same parallels in security research when it comes to finding malicious intent in the malware code that we are trying to analyze, and also in terms of tracking evolution of a malware variant or a malware family, like how it evolves over a period of time against the new defenses the security community is making against them. And it can also be used in vulnerability research, finding 0 days, and it can also be used in establishing the PHA code, basically potentially harmful applications code's intention for stealthy behavior. The whole structure of this particular talk is based on creating a very simpleton analogous example in a real world, and then mapping it into a security research world so that it would be easier for wider audience to understand the concepts. So here I'm first taking a very simpleton hypothetical drama where we are going to observe a set of events, and then we will be translating that into our graph analytics. Say the event one, a gardener bot called BT1 purchasing pesticides in the edible form, right? From some store called Warehouse One or something. And event two, a food delivery bot delivers food to some customer, Mr. ABC. And event three, the customer falls sick. And in event four, another entity, Mr. XYZ, has a gardener bot and the food delivery chain in their payroll. Now, if we translate these events to graph, uh, it would be something like this. So first I'm trying to filter all the person node in my graph. And as you could see, here there are only two person. And I'm expanding the relationship of the person Mr. ABC, and then I'm expanding the relationship of person XYZ, and I'm expanding the relationship of BT1. So now assume that this is an investigative scenario where we are trying to investigate what has happened. what has happened in this case. Um, we could come up with several conclusions. For example, we can easily use a graph to see how Mr. XYZ could have sabotaged the health of Mr. ABC, whether it is via the delivery aggregator partner that he has a relationship with, or could he have directly worked with BT2 to contaminate the food that Mr. ABC takes, or could he have used the service of BT1 to unknowingly contaminate the food Mr. ABC without the knowledge of BT2 or BT or the delivery aggregator, or whether all these parties are involved in this conspiracy, right? So how do we go about that? So basically, we can. That's where we will be able to use graph data science libraries, and some of the frequently used functionalities are like pathfinding, which can be used to investigate malicious behavior and finding fuzzing candidates in vulnerability research assignments, or community detection, which can be used in unsupervised clustering, or centrality, basically how important a particular node is in the whole scheme of things, and topological link prediction. And another very important and most frequently used algorithm is similarity, finding similarity, and not only finding similarity, finding dissimilarity or differences between, for example, two nodes may be 95% similar, but there are 5% of traits for a particular node which is totally unique when you compare with the related nodes. That marks a clear evolution happening in that particular malware family. So this malware variant is so similar to the known variants, but it still has a very fresh set of features or properties that exist only in this particular variant, not in the other similar variants. So similarity analysis serves two purposes. One is to find similar samples, and another one is to keep track of evolution that is happening. And so this is the pathfinding example applied in our hypothetical use case. We will be able to see how Mr. ABC is connected with the warehouse one, right? So now let us quickly jump to the real world or the malware research world, and how we can use some of these concepts in the day-to-day job of a malware researcher. So if we have to map the same hypothetical world to the real threat landscape, consider there are two applications. So one application requests permission to read contacts, and it reads contacts and stores in a log file. And say another application which is signed by the same entity of app1, it requests internet permission and it exfiltrates the log file generated by the app1. If you can recollect, app1 has actually dumped all the contacts in the log file. So essentially the net effect becomes an app stealing contacts from the phone. When we view these apps individually, when we analyze them individually without the knowledge of the other app, we will not be able to term it as a malware or a potentially unwanted application or a potentially harmful applications. But when we view them together as they collude, the net effect becomes malicious. So why we are advocating the use of knowledge graph? We all know, like, when the raw data, when we process them, it becomes information, and if we process information, it becomes knowledge, and then it can be translated into wisdom, right? That is what the research wisdom the person gains over a period of time. So basically, knowledge graph preserves and nurtures the context in the whole malware analysis stacks. Over a period of time, we may analyze so many malware over a period of years, and how the experience gets translated into the day-to-day tasks, how we use some of the knowledge we gained out of the experience. That context, if we store it in a simple database, might get lost. But when we represent our knowledge in the information we accumulated over a period of time as a graph, it helps us to provide the context for any researcher who leverages the knowledge graph. And of course, it enables tracking evolution. That's one of the easiest way to track how a particular malware family evolves over a period of time, and it promotes causal inference. And with proliferation of data in the information age, the answers are everywhere. Like we have all the answers in the form of data, but it is all about asking the right questions. And knowledge graph nudges the researcher, whoever uses it, to ask the right questions so that they can be directed to the correct direction. So, how to start building knowledge graph? One can start building a personal knowledge graph to aid individual researchers in individual tasks, or it can be a group context hub computing paradigm where we have a scalable repo and many people contributing to it with the analysis that they make. And it can be a combination of graphs. It can be static analysis graph, dynamic analysis graph, added with instrumentation kg, added with memory forensics knowledge graph, and observability knowledge graph. We will see some of these examples in the subsequent slides. For example, in the building static analysis model, say you are trying to build a static graph. So basically, the target that you are trying to analyze. For example, in this case, I have taken the example of analyzing Android files. So I have represented an APK as a graph with their key components like providers, services, broadcast receivers, um, and all that in the form of graph. And then each of those nodes have the subsequent children nodes, like their properties, some of their roles. So when you visualize or when you store the data in this graph shaped data format, we already leverage the time proven graph algorithms that can come handy and provide right information at the right time without the researcher explicitly asking for it, right? So that's the main goal of this. So we will see a quick demo. Maybe we'll see a live demo as well for this. Say now I have a empty database now, knowledge Neo4j graph, and as you could see, there are no labels, there are no relationship now. So let's try to use our parser that takes the APK as the input. And it parses it and it populates the knowledge graph. So now we can see there is an APK called demo ransom.apk, and if you see, it has a static analysis model and it has few nodes, so on and so forth. Now let us add another APK's information. So if we go back and see the APKs now, you should be able to see there are two APKs now. Let's add one more. Now we can go back and see that there are three APKs. Okay. Now we shall demonstrate how we can use one of the common similarity algorithm, GDS algorithm, and find how similar these APKs are, right? So let me quickly project it as a my graph N4. And stream the results. Yeah. So you could see here, the APK one with the hash value, this one is 0.46, 46% similar to this APK. And this APK is 0.01, that is 1% similar with this another APK, right? So if you quickly go back to our previous APK format, you will be able to see that. So this is the odd one out, like we have seen. This has 1% similarity, right? And you can expand. So if you see, these two belong to a ransomware variant category because it uses, as you could see in Android ransomware, the older ransomware, they generally use window layout parameters, and you could see the code or the attributes or the call chains which are shared between ransomware variants. And this is like a typical a vulnerable application created for an exercise purpose by somebody. So now you could see that these two samples has close to zero similarity with this application, but they share around 46% of similarity among each other. So since this is a demo, I chosen a very lightweight malware family. But in a real world use case, there will be hundreds and thousands of variants for each family, and they would have a very dense graph, which is better consumed via text format than the visualization format when we deal it in bulk, and that will clearly give the similarity analysis and then clustering and pathfinding when we try to find a new evolution tracking and all that stuff. So let's go back to our So this kind of analysis is very common, and in the blog we published previously about ransomware, uh, we have found how a new variant in the existing family has started a new feature using a new feature. Basically, if you see, these are the three different ransomware variants. This particular variant is abusing the accessibility features. This particular variant was abusing the system alert window feature, and there was this particular new ransomware variant which neither abused system alert window nor abused accessibility features, but it had come up with a new way of abuse, like abusing the notification services. So the rest of the code are similar. So this is what I was telling when I said it is not only important to focus on similarities, but also to focus on samples which are so close with each other yet so different. So this particular sample is so close and similar with these two variants, yet it had a new set of features which marked a clear evolution in the existing ransomware family that they belong to. Similarly, we can, like I have said, it can be a combination of multiple knowledge graphs to solve the security research problem in that particular platform. So in this case, eBPF, as we all know, is a very famous observability framework. So here what we are trying to do is we are running eBPF probes, and like we have seen in the previous exercise, how a parser parsed the APK file and populated the nodes. Here, the eBPF probes are monitoring the events happening across the system and converts those into the nodes and populates them in the graph database as we speak. So in this case, a ransomware, which is a multi-component Trojan, which drops a file, which downloads a file and then drops it in the target system and then executes it. So this particular whole execution is monitored by eBPF, and the eBPF has populated this graph. And like we have done in the previous exercise, we should be able to investigate what has happened, what transpired during the whole infection of ransomware, and we will be able to see that how a particular seemingly innocent executable, when it started executing, reached out to internet, pulled down as a primary payload, and that primary payload actually dropped the secondary payload, and if you expand the secondary payloads execution behavior, we will be able to complete the behavioral knowledge graph, like how it was overwriting all the existing files in the disk, and basically demanding the ransom from the victim. So now, not only the static knowledge graph, when the static knowledge graph combined with this behavioral knowledge graph built by eBPF, it provides an additional layer of context. And automatically, since everything is underwired with the primary SHA as the primary key for each APK, the graph automatically takes care of abstraction and providing the contextual information to complete the research about the malware that you are trying to analyze. And the third knowledge graph we are going to build is building KG using by leveraging volatility. Volatility is a open source memory forensics framework. So it is a very mature framework with a lot of support for custom plugins. So we are going to modify one of its plugins to bring this contextual graph analytics into it. So when a researcher wants to run a malware, dump the entire live memory, and then try to investigate it from the DFIR perspective, digital forensics perspective, um, we shall be able to use the same concept that we have been discussing so far. For example, I have already captured the memory image of the Android device, and now what I'm going to do is I'm going to call this vol.py, which is volatility, and we are invoking a plugin procmaps kg. Procmaps kg is nothing but a Python script that actually does the same thing what static analyzer did for static analysis and eBPF probes did for converting the eBPF observed events to Neo4j nodes. Similarly, it will take the volatility's output for process maps, and then it will plot it as a graph. So now you could see here that this particular graph has no labels or nodes. Now let's try to run this plugin. So while volatility produces all the parsed data structure and the proc maps, in the backend you could see that this particular process has been mapped as a graph. So now we combine all these three graphs, which will produce a static analysis graph combined with the eBPF graph and combined with this memory forensics volatility graph. It completes a circle for malware analysis, and then it will also be an awesome candidate to find vulnerabilities. Say when we try to analyze 0 days, when we try to identify fuzzing candidates for a particular component, or when we try to find paths between two functions. It has n number of use cases, and it is only limited to the imagination of the user. So let's quickly go back to So with that, I basically conclude how we can use some of the Neo4j awesome GDS capabilities and applied in security research and vulnerability research. If you have any queries, I would be happy to take them up.
Thank you, Dinesh. Let me see if there is any question. We still have some time left. I think, yeah, I can ask you some question. This whole thing looks very, very exciting. So, okay, I think you have done a lot of manual stuff to do like a memory forensic to check the trace of any attack or vulnerability issues. Do you think this, what am I trying to say? Do you think you can do make this more streamlined, like instead of doing a lot of manual operations, like loading files, running some scripts, to make it more streamlined and
yeah, we should be able to put everything in the framework, like for example an automation framework where we click a button which takes care of setting up the probes and then running the sample and collecting all these things. Yes, definitely that is that is possible. Yeah.
Right. I can certainly see once you show everything as a graph, right? The relationships, the similarity, the path becomes so obvious.
Yeah.
The other question may be sensitive. Let me have a look. Is anyone asking question in the channel? Right. Yeah. So yeah, this may be sensitive. Have you ever used this method to detect something in the real world?
Yeah, basically I try to play with all kind of graph algorithms, right? How basically I try to use mathematics for solving some of the problems that we face. So in one of the examples, I have shown how a ransomware which is so close with two other variants but yet so different, like it has come up with a new way to create a ransomware screen. So in that part, basically, I was trying to find how these malware evolve over a period of time. Yes, definitely.
Excellent. Okay, let's see if there's any other question.
So basically, for my personal work, I generally use so many new tools, so many new methodologies. For official, it may be different. Like we will use a standard set of tools, but for my personal work, I generally use so many number of tools.
Okay, I think it is probably very sophisticated. The people in trying to digest it. But that's okay. I think we can always bring this offline to follow up with Dinesh on any further questions. And again, thank you so much, Dinesh, for the great presentation and the demo.
Thank you.
And enjoy your day. Thank you.